Okay. So now having plotted the magnitude plot, once again please note that I am only plotting the asymptotes, right? We are not plotting the actual curve as such, right? So now let us go ahead and plot the phase plot. Okay. So let us do the phase plot. So let me draw the phase plot. So the phase of g of j omega I am plotting in degrees. Okay. So let us say I start with 0 and then let us say, so this is oops. Okay, let us say this is minus 90, let us say this is plus 90, fine. Okay. So once again we have 0.1, 1, 10, 100. Okay, so as the 4 regions. Now let us just plot the phase plot. Okay, so what is going to happen? Let us do it for each one factor at a time, right? That is what we are going to do. So let me use the same color code. So what happens to the see, ultimately what are we plotting for? G of s is going to be, let me rewrite the transfer function here. So 0.1 s divided by s plus 1 times 0.1 s plus 1, right? So that is what we are doing. Okay. So now what is going to be the phase contribution of 0.1? The phase contribution of 0.1 is going to be 0 degrees, right? So I draw a horizontal line at 0 degrees. Okay. So this is going to be the contribution from 0.1. What is going to be the contribution from s? Plus 90, alright. So that is going to be the same throughout the frequency range. So this is the phase contribution of s. What about the phase contribution of 1 by s plus 1? So if you recall, what happens with 1 by s plus 1 is that it's the low frequency value is 0. It has a phase of minus 45 degrees at the corner frequencies is 1, and then it tends to 90 degrees, minus 90 degrees as omega tends to infinity, right? That is the phase plot of 1 by s plus 1, right? So that is what I am going to plot. So at the corner frequency of 1, we are going to have a phase of minus 45. So what is going to happen is the following. So 1 by s plus 1 will have a phase plot like this. Okay, this is going to be the phase plot of 1 by s plus 1 in green. Now what is going to happen with 1 by 0.1 s plus 1 at the corner frequency of 10, we are going to have a phase of minus 45. Okay. So what is going to happen is the following. So we are going to have a phase diagram of 1 by 0.1 s plus 1 coming like this. Okay, so this is the phase diagram of 1 by 0.1 s plus 1. So now what we need to do is that if I want a phase diagram of the complete transfer function, I just need to add the 4 curves, right? But this is a little bit complex because these are not straight lines, all right? So it's okay, but the thing is that like at low frequencies you will start from plus 90 degrees. That's obvious, right? Because at very low frequencies, the only phase contribution will come from S, because 0.1 anyway will give you a phase contribution of 0 degrees throughout. 1 by s plus 1 and 1 by 0.1 s plus 1 will give you a phase contribution of close to 0 degrees at low frequencies. So, at low frequencies anyway I will start from the value of 90 degrees. So, if you in a sense look at the phase of g of j omega, essentially the formula for this is going to be 90 degrees, because that is what s will give me, minus tan inverse omega, that is what will be the phase of 1 by j omega plus 1, and tan inverse of minus tan inverse of 0.1 omega, because that is going to be the phase contribution of 1 divided by 0.1 j omega plus 1, right. So, I think this is something which we have discussed before, right. You have a transfer function as essentially products of terms, you just add the individual, take the algebraic sum of the individual phase contributions, right. So, that is what we have. So, what we do is that, like in order to plot the net phase plot, we just take the, we just calculate the phase at the corner frequencies, so that we can mark them and draw a smooth curve through those frequencies, right. So, the two corner frequencies are at omega equals 1 and omega equals 10. So, at omega equals 1, what is going to happen to this what to say value? We are going to have 90 degrees minus tan inverse 1 minus tan inverse of 0.1, alright. So, that is what we are going to have. So, what is the value? Can you calculate and tell me? Of course, tan inverse of 1 is 45. What is tan inverse of 0.1? So, if I calculate tan inverse of 0.1, that is around 5.71 degrees, right. So, 5.71 plus 45, okay, that is going to be the one. So, I subtract it from 90, I get 39.29, right. So, that is what I have. So, I get 39.29 degrees, okay, as the value at omega equals 1. So, at omega equals 1, the phase is going to be approximately, let us say something like 39, oops, okay, 39.29, okay. So, this value is something like 39.29, okay. So, that is the value. Now, at omega equals 10, what do we get? The phase of g of j omega is going to be equal to 90 degrees minus tan inverse of 10 minus tan inverse of 1, right. That is what we will have. So, tan inverse of 1, the third term now is 45 degrees. What is tan inverse of 10? Let us calculate. So, let us calculate tan inverse of 10 and then we will see what happens. So, tan inverse of 10 is this, then I add 45. Then I take the negative of this and then I add 90. So, I am going to get essentially the negative of the same number, I am going to get minus 39.29 degrees, that is what I am going to get, right. So, at 10 I am going to have something like this, okay. So, this is going to be minus 39.29. So, what I need to draw is that I need to draw a phase curve which essentially starts from 90 and then like passes through these two points, right, and then ultimately goes to minus 90, okay, as omega tends to infinity, okay. So, that is what will happen. Why minus 90? Because tan inverse omega will contribute a 90 degrees, tan inverse of 0.1 omega will contribute a 90 degrees. So, immediately you see that as omega tends to infinity, the phase of g of j omega will tend to minus 90 degrees, right. I hope it is clear, right. And as omega tends to 0, the phase of g of j omega, you can immediately see that it tends to 0 degrees, right. That is pretty obvious. So, that is why, sorry, not 0, 90 degrees, I am sorry about that, okay, plus 90, because the tan inverse, two tan inverse terms will contribute 0, you already have a 90 degree term. So, we have 90 degrees. So, you see that the phase curve goes from 90 plus 90 to minus 90 in this manner, okay. So, this is the phase curve of this net transfer function. So, the red one is a phase of g of j omega. Okay, so that is the phase plot for this particular transfer function. And you immediately see that because this has a 0 at 0, okay, it does not have a 0 in the right of plane, it essentially follows the points that we discussed at the beginning of this class, right. What did we discuss? You give me a transfer function, right, and I plot the Bode diagram, you immediately see that the magnitude plot is going to tend to a slope of minus 20 times n minus m decibels per decade. What was n minus m in this problem? What is n? 2, m 1 in this particular problem, right, because this is the transfer function we started off with, okay, isn't it? Okay, so you see that n minus m is 1 in this case. So what did the magnitude plot slope tend to at high frequencies? Minus 20 decibels per decade, one could see that, right. So that was the general concept that we learned, and since this is a minimum phase system, what did the phase tend to? Minus 90 degrees times n minus m. You see that it tends to minus 90 degrees, okay. So this is the procedure for calculating the Bode plot, right. So given the particular transfer function, okay. We should be also familiar with the inverse process. Let us say I give you this Bode plot, can you figure out the transfer function? Okay, that plays a very important role, okay, like as far as experimental determination of transfer function is concerned. And towards the end of the course, we will do a case study in that regard, okay. So I will give you the reason I am letting you do all the experiments is I want to see, like how much you gain out of those experiments, okay. So I want you to independently think, and then like what I will do is that I will give you actual data from one of those experiments and then ask you to get the transfer function, okay. Some techniques you may be already reading, learning in some of the experiments, okay. So but then like let us see towards the end, okay, like so how the theory and practice come together, okay. See, right now we are looking at many mathematical formulations and ideas and so on, right. So using frequency response, towards the end you will see how everything comes together, okay, for practical applications, okay. So that's something which we look at in the maybe the last 2 weeks of the course, right. So we will do a few case studies, okay. So that's something which we will keep for the end, okay. So this is the Bode plot, and it becomes very important because what happens is that like many times if you want to experimentally determine the transfer function of the system, right. Let us say what we have been doing in this course, we have been using physics to derive mathematical equations in the form of linear ODEs, then take Laplace transform, then get the transfer function, right. Suppose like we want to do the same process empirically, that is I do not want to derive equations of motion, or I am not in a position to derive equations of motion because my system which is given to me is like a black box. I do not know what components are there, so I cannot, I am in a position not to apply physics to model the system. Then what I do is that I can use frequency response to my advantage, right, isn't it? I can use experiments to my advantage, right. I can give sinusoids of varying frequency, I look at the steady state output. If I also get sinusoids of the same frequency, then I know that in a frequency range of interest I can model the system as an LTA system, right. That is point number 1. And then what you do is that then you record the input sinusoid, output sinusoid, you know what is the scaling, okay, you know the input amplitude, output amplitude, you will get the magnitude at particular frequencies. You can also measure the phase shift, right, then you get the phase plot, then you plot the magnitude plot, plot the phase plot, you get the Bode plot, right, and you do the inverse problem, that is given the Bode plot, how do you get the transfer function, okay. That is something which you can figure out, right. So that is an important practical application of what we are learning, okay, as far as the Bode diagram is concerned, right. So anyway, I will give you a few more Bode diagrams to plot as homework, okay. So but right now, you know, like what I am going to leave you with is a bunch of is a set of questions, right. So, I am going to ask you a question, okay, please think about it and try to figure out the answers, okay. Using the Bode plot, okay, Bode plot, how can one calculate the values of KPE, KVE and KAE. Okay, I think I am using the, I hope I am using the same symbols, right. So, KPE was the static position error constant, KVE was the static velocity error constant, KE was the static acceleration error constant. You remember when we did steady state error analysis, please refer to those notes, right. I am hoping that I am using the same symbols, okay. Okay, so the question is that, like, I am going to leave you with is that, like, how do we calculate these constants, right, when we have the Bode plot. Let us say I give you the Bode plot, can you use the Bode plot to graphically figure out these constants, and what is the advantage of this, because using the Bode plot you can tell me what is going to be the steady state error, right, when you have certain types of inputs, right. So, that is something which I want you to figure out. Okay. So, I am just going to stop here, okay. Like, so with this we complete our discussion of Bode plots. So, in the big picture perspective, what we are doing frequency response, right. Essentially what happens when we give sinusoidal inputs to stable LTI systems, we saw that the steady state output is also going to be a sinusoid of the same frequency, but scaled in magnitude and shifted in phase, right. So, and the term which is important is what is called as sinusoidal transfer function, right. So, which we get by substituting S equals j omega in the system transfer function, okay. Now, the question is how do we visualize that sinusoidal transfer function so that we can do frequency response analysis. One of the main tools which you will use in multiple domains, including automotive and biomedical, which are the groups of interest for our department. One of the main tools we use is what is called the Bode plot. Okay, that is why I spent quite a bit of time in explaining the Bode plots. Okay. So, next week what I am going to do is that, like, I am going to briefly discuss what is called as a Nyquist plot and the Nyquist stability criteria. I am not going to spend so much time on that, okay, but I want you to know what they are, right. And then, like, we will go to essentially controller design using frequency response methods. Okay, we did control design using time response methods. Now we are going to use frequency response methods to design controllers, and then we look at both. Okay, so that's what our action plan is. Fine.